how one shipbuilder's impossible hull design kept a burning carrier alive. In the Pacific, March 19, 1945, 50 mi off the coast of Honshu, Japan, the steel deck trembled beneath Lieutenant Commander Joseph T. O'Callahan's feet as he watched the flight crews prepare the morning strike. The Catholic chaplain had been awake since 0400, celebrating Mass for the early watch in the dimly lit wardroom. Now as dawn broke over the Pacific, he stood near the island superstructure, watching ordnance men load the massive Tiny Tim rockets onto Corsair fighters. Each 11 FT rocket carried 500 lb of high explosive, enough to crack open a battleship's armor. They had never been used in combat before. Franklin would be the first carrier to launch them against the Japanese mainland. What Father O'Callahan didn't know was that in less than 3 hours, his ship would become a floating inferno that defied every prediction of destruction. USS Franklin would suffer damage that naval architects had calculated would send any carrier to the bottom within minutes. She would lose 87 men in an instant, more casualties than any American warship would survive. Her flight deck would become a holocaust of exploding ammunition and rockets. Her hangar deck a furnace where temperatures reached 2,000 degrees Fahrenheit. Yet she would not sink. Against every law of naval warfare, against every expectation of material science, she would survive. And the reason for her survival had been built into her bones 5 years earlier, in a Virginia shipyard, by men who had been told their innovations were impossible. The morning of March 19th had begun with the routine tension of combat operations at the edge of Japanese home waters. Task Force 58 had been striking targets around Kyushu and Honshu for 3 days, softening defenses before the April 1st invasion of Okinawa. Franklin, as part of Task Group 58, 2 under Rear Admiral Ralph Davidson, had moved closer to Japan than any American carrier had dared. At 50 mi from the coast, she was well within range of land-based aircraft. Captain Leslie E. Garras, commanding officer since November 1944, had pushed his ship forward aggressively. Some crew members whispered that Garras, nicknamed Custer for his aggressive tactics, was taking unnecessary risks, but the mission required it. The closer Franklin operated, the more sorties her aircraft could fly, the longer they could remain over target. Franklin had launched her first strike at dawn. 12 Corsair fighters and 16 Avenger torpedo bombers roaring off the deck to hit airfields around Kobe. The second strike was spotted on deck, ready to launch. 31 aircraft sat with engines warming, propellers turning, pilots in cockpits running final checks. The deck was a carefully choreographed dance of controlled danger. Ordnancemen had loaded the experimental Tiny Tim rockets, wrestling the massive weapons onto wing pylons. Aviation gasoline trucks had just finished topping off fuel tanks. In the hangar deck below, 22 more aircraft waited, 16 of them fully fueled, 5 armed with bombs and rockets for the next launch cycle. It was the most vulnerable moment in carrier operations when hundreds of tons of aviation gasoline and ordnance sat exposed on 2 decks simultaneously, when a single spark could trigger catastrophe. At 07:08 hours, 7 minutes after 7 in the morning, a lone Yokosuka D-4Y Judy dive bomber appeared through the cloud cover at 2500 Tarawera. The ship's radar had not detected it amid the clutter of returning American aircraft. The combat air patrol, focused on threats from other vectors, had not intercepted it. The anti-aircraft gun crews, tracking multiple contacts, had no time to train their weapons before the Japanese pilot committed to his dive. His name would never be known. He had perhaps 30 seconds from the moment he pushed over until impact. In that half-minute, he released 2 550 lb semi-Aurora-piercing bombs with devastating accuracy, then vanished back into the clouds before anyone could track him. He had achieved what every Japanese aviator dreamed of, a perfect attack run against an American carrier. Whether he survived to report his success remains unknown. The first bomb struck the flight deck center line 15 ft forward of the island superstructure. It punched through the 3-in wooden planking as if it were paper, then through the steel deck beneath and detonated in the hangar deck. The blast wave, traveling at 26,000 ft/s, tore through the packed aircraft like a giant fist. Aviation gasoline ignited instantly, creating a fireball that engulfed everything within 50 ft. The explosion sent the number 1 elevator, a 4-ton steel platform measuring 60 ft by 34 ft, rocketing upward out of its shaft like a missile. It rose 400 ft into the air, tumbled end over end, then crashed back onto the deck, shattering into fragments that tore through aircraft and men alike. Secondary explosions rippled across the hangar as fuel tanks ruptured and ordnance cooked off. The second bomb hit aft among the 31 aircraft warming up for launch. It detonated on contact with the flight deck, creating an instant holocaust. 31 fuel tanks exploded in sequence, each one adding to the fireball that rolled across the deck like a breaking wave of flame. Men on nearby ships later said they felt their vessels rock from the force of the explosion. The blast wave knocked sailors off their feet on destroyers 1,000 yards away. On Franklin's flight deck, pilots trapped in their cockpits had no chance. Some managed to unbuckle and dive overboard. Others burned where they sat, their screams lost in the roar of exploding fuel and ammunition. What happened in the next 30 seconds determined whether Franklin would live or die. In the hangar deck where the first bomb had detonated, fires spread with terrifying speed. Gasoline from ruptured fuel tanks ran across the steel deck, seeking any opening. It found the ventilation ducts. Within seconds, burning gasoline vapor was being pumped throughout the ship by the ventilation system, still running on automatic. The heat ignited ready ammunition stored near the aircraft. 20mm rounds began cooking off, their red traces streaking through the smoke like deadly fireflies. 40mm shells exploded with the force of grenades hurling shrapnel through the hangar. Men trying to reach firefighting equipment were cut down by their own ammunition. And then the tiny TIM rockets began to ignite. These massive weapons, each weighing $2,300 BN, were still experimental. No one knew how they would behave in a fire. The solid fuel motors were designed to burn at 5,000 degree F for 6 seconds, producing 50,000 lb of thrust. When the first one ignited at 7:11, 3 minutes after the initial attack, its motor came to life with a shriek that could be heard over the roar of fire and explosion. The 11 FT missiles shot across the deck horizontally like a meteor, trailing flame. It punched through the 0.5 and steel plating of the island structure as if it were tinfoil and exploded on the starboard side, showering the deck with molten metal and fragments. More followed. Rockets screamed in every direction, some plunging into the sea, others smashing through bulkheads, one cutting a gun crew in half before exploding in the water. Another rocketed the length of the flight deck and disappeared over the bow. The flight deck became a killing ground where men died from fire, explosion, or the random trajectories of weapons designed to destroy enemy ships. Lieutenant Commander Stephen Jurica Jr., the ship's navigator, was in his sea cabin just below the bridge when the first bomb hit. A 1930 Naval Academy graduate who had served as intelligence officer on USS Hornet during the Diddle raid, Jurica knew immediately what had happened. The distinctive double thump of bomb detonations followed by the rolling thunder of secondary explosions told the story. He grabbed his life jacket and battle helmet and ran for the bridge. What he saw when he emerged topside would haunt him for the rest of his life. The after 2/3 of the flight deck was a sea of flame. Aircraft were exploding, some launching themselves into the ocean as their engines caught fire and ran at full throttle, propellers screaming. The wooden deck planking was burning, adding to the inferno. Holes gaped where bombs and rockets had penetrated, some large enough to fall through. Men were on fire, running, rolling, jumping over the side. The list to starboard was already noticeable, perhaps 5 degrees and increasing. Black smoke boiled from the hangar deck openings, so thick it obscured the after part of the ship. And every few seconds another tiny TIM rocket would ignite and scream across the deck on an unpredictable trajectory. Jurica began organizing damage control parties from stunned survivors. The forward section of the flight deck was still relatively clear. If they could create a fire break, if they could keep the flames from spreading forward, they might save the bow section. But the afterflight deck, where 31 aircraft had been spotted for launch, was beyond saving. Jurica made one of the hardest decisions any officer ever makes. He ordered all personnel to abandon the afterflight deck, concentrate all efforts on saving the forward 2/3 of the ship. It meant leaving wounded men behind. It meant letting fires burn that might have been fought. But it meant focusing desperately limited resources where they might make a difference. In the engineering spaces 4 decks below, Lieutenant Junior Grade Donald Arthur Gary was standing his watch as engineering officer in the forward engine room when the bombs hit. A 1943 Naval Academy graduate, Gary had been aboard Franklin for less than 4 months, but those 4 months had included the October 30th, 1944 kamikaze attack that killed 56 men. He knew what carrier damage looked like. He felt the ship shudder twice, felt the shock waves transmitted through the hull structure, heard the immediate roar of secondary explosions. The engineering watch standers looked to him for orders. Gary's first priority was keeping the plant running. Franklin had been making 25 knots, her 8 Babcock and Wilcox boilers delivering maximum steam through 4 turbines to the propeller shafts. Now explosions on the flight and hangar decks were sending shockwaves through the ship. Fuel oil lines ruptured, steam lines fractured, and most critically, the ventilation system began pumping smoke into the engineering spaces. In a conventionally designed ship, the engineering crew would have had 2 choices: abandon the machinery spaces and lose all power, or stay and suffocate. Gary saw a third option. The extensive compartmentalization built into the Essex-class design meant the forward engine room could be isolated from the rest of the ship. He ordered his crew to seal all ventilation ducts immediately. Emergency breathing apparatus was broken out. Portable air bottles normally used for firefighting. The men would breathe from bottles while they worked. Then Gary made a systematic evaluation of what still functioned. Of the 8 boilers, 2 in the forward boiler room were still operational. 3 of the 4 turbines could still turn the shafts. The electrical system was failing in sections as fires burned through cables, but generators in undamaged compartments were still running, and the electrical ring main system allowed power to be rerouted around damaged sections. Gary made the decision that would save the ship. Instead of abandoning his station, he would keep the engineering plant running. As long as Franklin had power, she had a chance. Power meant pumps for firefighting. Power meant ventilation for damage control parties. Power meant steering control. And ultimately, power meant propulsion. A ship that could move under her own power had options a dead ship did not. But his crew was suffocating. The smoke infiltration was too great. The portable air bottles wouldn't last. Gary remembered something from his engineering training and from the ship's construction specifications. The CO2 system designed to flood fuel storage compartments in case of fire could theoretically be jury-rigged to provide positive pressure ventilation. It was a theoretical possibility that had never been tested. The system was designed to pump carbon dioxide, which would kill them instantly. But if he could isolate the CO2 bottles and instead use the high-press air bottles from the damage control system, he might be able to flood the engine room with breathable air under positive pressure, forcing the smoke out through the sealed ventilation ducts. With his crew on the edge of collapse, Gary began manually routing valves and pipes, converting a fire suppression system into a life support system. His hands shook from lack of oxygen as he worked. Finally, he opened the valve. High-pressure air flooded the space, the pressure gauge climbing. The sealed hatches held. Smoke began venting through the small gaps around the ventilation dampers. Within 2 minutes, the air cleared enough to breathe. The forward engineering spaces, sealed and pressurized, became a habitable island in a ship filled with death. On the hangar deck, Father O'Callahan had been blown off his feet by the first explosion. The 43-year-old Jesuit priest, who before the war had been a physics and mathematics professor at Holy Cross College in Worcester, Massachusetts, found himself lying in burning gasoline. His uniform was on fire. He rolled, smothering the flames, then struggled to his feet. Around him, the hangar deck had become hell. The hangar deck was essentially a steel box 654 ft long and 70 ft wide with a ceiling height of 17 ft 6 in. The overhead was a maze of pipes, cables, and ventilation ducts. Now that entire space was filled with flame and smoke. Aircraft were burning, their aluminum skin melting and dripping like wax. Ammunition was exploding continuously, a staccato roar punctuated by the shriek of tiny TIM rockets. The heat was so intense that the 2-5 and special treatment steel plates of the hangar deck were beginning to glow red in spots. O'Callahan understood what he was seeing, even though the implications seemed impossible. The hangar deck wasn't collapsing. The STS plates weren't warping or buckling, despite temperatures that should have melted mild steel. The fire, horrific as it was, remained largely confined to the hangar level. It wasn't burning through to the third deck below. The steel wasn't failing. The ship's structure was holding. O'Callahan, his white chaplain's helmet, marked with a black cross, began moving through the flames. He gave last rites to dying men, his voice raised above the roar. Through this holy anointing, may the Lord in his love and mercy help you with the grace of the Holy Spirit. May the Lord who frees you from sin save you and raise you up. Then he began organizing survivors. Men were standing around stunned, waiting for orders. O'Callahan gave them orders. Form a bucket brigade. Ammunition over the side before it cooks off. Wounded men to the forward elevator. Hoses from the fire main. The hangar sprinkler system was damaged, its pipes torn by shrapnel. but portable pumps could still draw from the 4 independent fire main systems. Men hauled hoses toward the flames, the rubber hoses so hot they burned through gloves. Others began throwing burning aircraft over the side through the hangar deck openings, using tractors to push the flaming wreckage through the 60-t wide doors. O'Callaghan, moving through fire that melted the soles of his shoes, directing efforts with the calm authority of a mathematics professor explaining a theorem, became a legend in those minutes. Years later, survivors would remember him as a figure from medieval legend, a warrior priest who seemed immune to fear. But O'Callaghan later told interviewers that he was terrified every moment. What kept him moving was a simple realization: the ship was surviving, despite everything, despite fires that should have caused catastrophic structural failure, despite explosions that should have broken her back. Franklin was still afloat. If the ship could hold together, he could hold together. On the bridge, Captain GZ was organizing the command response. The 54-year-old officer, who had entered the Navy as an enlisted man in World War I and worked his way up to naval aviator in command, understood immediately how desperate the situation was. All radio communications were dead, cut by fire. The Combat Information Center was destroyed. The radar systems were failing one by one as fires reached their electronic components. The ship was taking a list to starboard, now approaching 10 degrees. Fire was spreading despite desperate efforts to contain it, and most ominously, reports from Damage Control Central indicated that fires were burning in multiple compartments from the hangar deck down to the 3rd deck. Franklin was burning from the inside out. Gears made the first of several controversial decisions. He ordered all non-essential personnel topside and prepared to abandon ship if necessary. Hundreds of men poured up from below, some burned, some wounded, many simply terrified. They gathered on the forward flight deck and the folio away from the flames. Some jumped overboard without orders, choosing the ocean over the fire. Others were blown overboard by explosions. Within 20 minutes of the attack, over 800 men were in the water, swimming away from the burning hulk or clinging to debris and life rafts. The cruiser USS Pittsburgh, Captain John E. Gingrich commanding, was steaming 500 YD off Franklin's port beam. Gingrich maneuvered his ship to shield Franklin from the Japanese coast and to prepare for towing operations. By 07:30, just 22 minutes after the attack, Pittsburgh had passed a steel towing cable to Franklin and began taking her in tow, pulling her away from the Japanese coast at 5 knots. It was agonizingly slow, but it was movement. The cruiser USS Santa Fe, Captain Harold C. Fitz commanding, made an incredibly brave maneuver. He brought his 10,000-ton cruiser alongside the burning carrier, starboard side to take off wounded and non-essential personnel. With fire and explosions occurring every few seconds on Franklin with the carrier listing toward his ship, Fitz held Santa Fe in position for over an hour. As the two ships ground together, rolling in the swells, men jumped across the gap from the carrier to the cruiser. Others were lowered on stretchers. Santa Fe's crew formed rescue parties that actually boarded Franklin to help carry wounded to the rail. By the time Santa Fe pulled clear at 900, she had rescued 832 men from Franklin, including 103 wounded. Her white-painted hull was scorched black from the heat. Her superstructure dented where she had ground against the carrier, but she had saved 832 lives. At 800, 2 hours after the attack, Franklin's situation seemed hopeless to observers. She was dead in the water except for Pittsburgh's tow. She was listing 13 to starboard. Fire and smoke engulfed her from the island structure aft. Explosions continued as ammunition cooked off. The forward elevator, blown out of its shaft, lay twisted across the deck. The after elevator had been blown completely off the ship. Holes gaped in the flight deck some 20 ft across. Radio Tokyo, monitoring American communications, announced that a large American carrier had been sunk off Japan. Japanese submarines in the area received orders to find and finish off the wreck. Every man still aboard Franklin, every observer on the surrounding ships knew they were watching a death agony. Carriers didn't survive this kind of damage. Everyone knew that. But in the forward engine room, Donald Gary was achieving something extraordinary. Working with his engineering crew, breathing pressurized air in their sealed compartment, Gary had restored steam pressure to 2 of the forward boilers. He had 3 turbines operational. The electrical system, jury-rigged through emergency damage control cables, was providing power to critical systems throughout the forward part of the ship. At 0800, Gary reported to the bridge via sound-powered phone. The only communication system still working. Bridge forward engine room. I have steam on 2 boilers. 3 turbines operational. Can make turns for revolutions equivalent to 2 knots. 2 knots was almost nothing. Barely walking speed, but it was propulsion. Captain Garris, on receiving this report, made his most important decision. He ordered Pittsburgh to cast off the tow. Franklin would move under her own power. It was a decision that shocked everyone who witnessed it. A carrier dead in the water, burning, exploding continuously, couldn't possibly make way. The idea seemed insane, but Garris understood something fundamental. A ship that could move had a chance. A ship under tow was helpless. A ship under her own power could maneuver, could create airflow across the deck to blow smoke and heat away, could restore stability through speed and rudder control. At 082, Franklin's massive bronze propellers began to turn. The engineering crew had managed to restore power to the starboard shafts. The ship, moving at barely 2 knots, began to inch away from the Japanese coast. It was one of the most remarkable moments in naval history. A carrier that should have sunk was moving under her own power. The restoration of propulsion transformed everything. Movement, even slow movement, created wind across the deck. The 25-knot winds generated by the ship's motion helped blow smoke and heat overboard instead of down into the ship. The improved airflow helped damaged control parties operate. The list began to improve as the engineering crew carefully controlled counter-flooding, deliberately flooding portside compartments to balance the thousands of tons of water that had accumulated on the starboard side from firefighting efforts. Most importantly, the fact that the ship could move gave the crew hope. Men who had been preparing to abandon ship returned to their stations. If Franklin could move, she could be saved. On the flight deck, Commander Jerica and his damage control parties had erected a water curtain across the deck at frame 110, about 400 ft from the bow. Using every available fire hose, they created a barrier of spray between the forward section they had to save and the fires aft that they could not yet control. The water curtain, an innovation built into the Essex-class design, worked exactly as planned. The wall of spray absorbed radiant heat and knocked down smoke, creating a defensive line firefighters could hold. Behind that barrier, the forward flight deck remained relatively intact, but Franklin wasn't out of danger. At 08:45, one of the worst secondary explosions occurred. A magazine filled with 5 in ammunition detonated below the hangar deck. The blast was catastrophic. Men on screening destroyers thought Franklin had finally blown up. A fireball rose 500 ft above the ship, a tower of flame and smoke visible for 20 meter. The explosion killed dozens of men who had been fighting fires in that section. It blew a hole through 3 decks from the hangar deck down to the 3rd deck. Fragments tore through spaces that had been undamaged, starting new fires, wounding more men. But something remarkable happened. The bulkheads around the magazine, all constructed of special treatment steel, contained most of the blast. In a conventionally built ship, the explosion would have torn through mild steel bulkheads and spread destruction laterally, probably breaking the ship's back. The fragments would have torn through adjacent spaces, detonating other magazines in a cascading catastrophe. But the STS bulkheads, designed to resist fragmentation, channeled the explosion upward and outward instead of sideways. The adjacent magazines remained intact. The fire mains running through that section were severed, but the redundant mains in other sections continued to supply pressure. The ship shuddered from the blast, but her structure held. By 1,002 hours and 52 minutes after the attack, Franklin had begun to stabilize. The fires were contained if not controlled. The list had been reduced to 9 degrees through careful counterflooding. The engineering plant was delivering enough power for 4 knots, then 6, then 8. By noon, Franklin was making 15 knots. The transformation was stunning. A carrier that observers had watched dying was now moving at respectable speed. Her fires mostly controlled, her crew beginning to organize recovery operations. By 1600, 8 hours after the attack, the major fires were out. Smoke still poured from the wreckage, and small fires continued to flare as damage control parties found new pockets of burning material. But the Holocaust was over. Franklin had survived. The cost was staggering. According to the most recent research by naval historians, 87 men had been killed, most in the first 10 minutes. Another 487 were wounded, many with burns that would require months of treatment. More than 30% of her crew was dead or wounded. But she was afloat, she was moving, and she was heading for safety. Captain Garris pointed the bow southeast toward Ulitheatl, 2,500 men away. Franklin, Escorted by Pittsburgh and screening destroyers began the long journey home. Her top speed was initially 15 knots, though as the engineering crew made repairs and brought more boilers online, she would eventually achieve 25 knots. She could make it. The voyage to Ulithi tested every aspect of the design philosophy that Homer Lenoir Ferguson had championed 5 years earlier. Franklin was a floating wreck, barely seaworthy, listing with massive holes in her deck and hull, but she remained afloat because her structure held. The hangar deck, subjected to fires that had reached 2000 degree F, showed severe warping, but no catastrophic buckling. The beams supporting the deck had deformed from the heat, but had not failed. The flight deck, holed in 53 places, still supported the weight of damage control equipment and the hundreds of men working to make temporary repairs. The hull plating stressed by the list, the explosions, the counter-flooding maintained watertight integrity. Most remarkably, the underwater protection system designed to resist torpedo hits but subjected to enormous shock loads from internal explosions remained intact. Not a single critical bulkhead in the underwater protection system failed. Franklin reached Ulithi on March 24th, 6 days after the attack. She anchored in the lagoon, a floating morgue carrying 87 bodies, but she had arrived under her own power. Temporary repairs were made over 4 days, primarily patching the flight deck holes and making the after section of the ship weathertight for the transit to Pearl Harbor. On March 28th, Franklin departed Yulee for Pearl Harbor, still capable of 20 knots despite her damage. She arrived at Pearl Harbor on April 3rd, causing a sensation. Word of her survival had spread through the Navy, but seeing the battered carrier enter the harbor under her own power was still stunning. The Navy made temporary repairs sufficient for the long transit through the Panama Canal and across to the Atlantic. On April 10th, Franklin departed Pearl Harbor on her own power, bound for the Brooklyn Navy Yard in New York. She arrived there on April 28th, 1945, nearly 6 weeks after the attack. At Brooklyn, the full extent of the damage could be assessed by Navy engineers and Bureau of Ships experts. War Damage Report number 56, compiled over the following months, documented the devastation. The hangar deck had been completely destroyed across 40% of its area. The flight deck was holed in 53 places with holes ranging from 3 ft to 20 ft in diameter. Over 30% of crew berthing spaces were burned out completely. The steel bulkheads warped by heat. Everything inside reduced to ash. Thousands of structural members needed replacement. The ventilation system had to be completely rebuilt. The electrical system required extensive reconstruction. The damage was so severe that repair would take 2 years at minimum and cost nearly as much as building a new carrier. But the basic structure was sound. Naval constructors examining the keel found it straight to within tolerances. The hull plating maintained integrity despite the fires and explosions. The engineering spaces, though damaged by smoke and some structural deformation from the heat, were repairable. The frames and structural members showed stress but no catastrophic failure. Franklin could be rebuilt. She would never be rebuilt because the war ended before repairs began, but she could have been. That itself was remarkable. The Navy made a different decision about Franklin's immediate future. She represented the most heavily damaged aircraft carrier to survive the war, a floating laboratory of battle damage. Rather than beginning immediate repairs, the Navy decided to use her as a testbed for understanding how carriers survived catastrophic damage. For months, engineers crawled through her wreckage, measuring, photographing, testing. They documented how special treatment steel behaved under extreme heat, measuring the deformation of structural members and the temperature gradients that had existed during the fire. They mapped how the blast effects from the magazine explosion had been contained by STS bulkheads. They studied how the multiple independent fire mains had maintained pressure, even when large sections of the ship were destroyed. Every piece of data was collected, analyzed, and incorporated into a massive report that would inform every carrier designed after the war. But Franklin's survival wasn't the only validation of the Essex-class design. The class would prove itself in battle repeatedly during the final months of the war. USS Bunker Hill, hit by 2 kamikaze aircraft on May 11, 1945 off Okinawa, suffered damage that killed 396 men and wounded 264 more. The attacks came within 30 seconds of each other. The first kamikaze crashed into planes being refueled on the flight deck, causing massive fires similar to Franklin's. The second hit penetrated to the gallery deck, spreading fire to interior spaces. Bunker Hill's damage control teams fought fires for 5 hours before bringing them under control. She too survived, making it back to port under her own power. Like Franklin, she was so heavily damaged that she never saw post-war service, but she didn't sink. USS Intrepid survived 4 separate kamikaze hits during the war. Hit on October 29, 1944. She was repaired and returned to service. Hit again on November 25, 1944. Repaired again. Hit a third time on March 18, 1945. Hit a fourth time on April 16, 1945. Each time her crew fought fires, made repairs, and returned to combat operations. She survived the war and served until 1974, finally being decommissioned after 31 years of service. She is now a museum ship in New York City. USS Enterprise, designated the Big E, became the most bombed, torpedoed, and otherwise damaged aircraft carrier in World War II that survived. Hit by bombs at Eastern Solomons, Santa Cruz, and in other actions nearly sunk by kamikaze attacks in May 1945. Each time, her Essex-class structure and damage control systems saved her. She survived the war and served until 1947. USS Hancock, USS Belleau Wood, USS Lexington, USS Wasp, USS Ticonderoga, USS Randolph, all took serious battle damage and survived. The common thread was the Essex-class design. The extensive use of special treatment steel, the comprehensive compartmentalization, the redundant firefighting systems, the careful design that made every structural element contribute to survival. None of these carriers sank. None was abandoned. All made it home. This wasn't luck. This was engineering. The contrast with carriers built to different standards was stark and well documented. The British armored carriers, which many pre-war experts had predicted would be more survivable than American designs, proved less resilient in practice. Their armored flight decks, made of 3-in thick armor plate, prevented bombs from penetrating to the hangar. But when fires did start in the hangar from other causes, they were extraordinarily difficult to fight because the armored deck above and armored hangar sides below created an oven that contained heat and smoke. The ventilation systems couldn't handle the heat. Firefighting parties couldn't operate in the conditions. Damage that an Essex-class carrier could repair in days kept British carriers out of action for weeks. HMS Formidable was hit by kamikazes twice in 1945. The armored flight deck prevented penetration, but fires in the hangar caused by burning gasoline from the crashing aircraft forced the ship to withdraw from operations both times. HMS Illustrious was knocked out of action repeatedly by damage that would have been considered moderate by Essex-class standards. HMS Victorious, HMS Indomitable all suffered similar problems. The British carriers were tough, but their armor philosophy made them less adaptable, more vulnerable to mission kill even when they survived the initial impact. The Japanese carrier force, which had begun the war with some of the finest carriers in the world, suffered from design limitations imposed by treaty restrictions and lack of combat experience. At Midway in June 1942, 4 Japanese fleet carriers were sunk by bomb hits that an Essex-class carrier would likely have survived. Akagi, Kaga, Soryu, and Hiryu all went down after being hit by 1,000 lb bombs that penetrated to their hangar decks and ignited fuel and ordnance. The Japanese carriers lacked adequate compartmentalization. Their firefighting systems were primitive compared to American designs, and they had minimal structural protection. They were essentially floating bombs. Once the cascading explosions started, there was no way to stop them. By 1945, Japan had no fleet carriers left capable of offensive operations, while America had 20 Essex-class carriers operational in the Pacific. The statistical record of the Essex-class speaks to Ferguson's vision with brutal clarity. 24 ships of the class were completed, 14 saw combat in World War II. They were hit by bombs, torpedoes, and kamikaze aircraft a total of 39 times. They suffered damage that killed over 2,600 men total across the class. Not one sank. Not one was abandoned as a constructive total loss. Every damaged Essex-class carrier was repaired and returned to service except Franklin and Bunker Hill, which were kept in reserve after the war ended because repairs weren't urgently needed. The class earned a total of 143 battle stars. They served in every major Pacific campaign from Tarawa to Tokyo Bay. But who was the man behind this remarkable design? Homer Lenoir Ferguson was born in Westville, North Carolina on March 6, 1873. At age 15, He entered the United States Naval Academy at Annapolis, an unusually young midshipman even for that era. He graduated in 1892, reportedly at the head of his class, though some sources suggest he graduated third. The records are ambiguous. What is clear is that he graduated with honors and was immediately selected for advanced study. Instead of going to sea, he was sent to Glasgow University in Scotland from 1892 to 1895 to study naval architecture and marine engineering under the renowned Scottish ship designers who were then leaders in the field. Glasgow in the 1890s was the center of the world shipbuilding industry. Scottish yards built the fastest, most advanced ships afloat. Ferguson studied under professors who had designed blockade runners for the Confederacy during the American Civil War. Fast ships that used iron frames and innovative hull designs. He learned stress analysis, hydrodynamics, metallurgy, and structural design. He absorbed the Scottish philosophy that ships should be built to survive, not just to be fast or heavily armed. A ship that sinks cannot complete its mission, his professors told him. Build ships that survive. Ferguson returned to the United States in 1895 and began a career as a naval constructor. He worked at the Columbian Iron Works in Baltimore, then at Navy Yards in Portland, Oregon, Breton, Washington, and Bath, Maine. He supervised construction of battleships and cruisers, learning the practical realities of how ships were actually built versus how they were designed on paper. In 1902, he joined Newport News Shipbuilding, then a relatively small yard in Virginia that had been founded by railroad magnate Collis P. Huntington in 1886. Ferguson started as assistant superintendent of construction. His engineering skill and leadership ability were immediately apparent. In 1905, at age 32, Ferguson resigned from the Navy to become a full-time civilian employee at Newport News. He rose rapidly through the company. By 1914, he was vice president under President Albert Lloyd Hopkins. On May 7, 1915, Hopkins was traveling to England on shipyard business aboard RMS Lusitania when the liner was torpedoed by a German submarine off the Irish coast. Hopkins died when the ship sank, one of 198 victims. Ferguson, who had been expected to someday succeed Hopkins, was suddenly thrust into leadership. On July 22, 1915, at age 42, Homer Ferguson became president of Newport News Shipbuilding. He would hold that position for the next 31 years through World War I, the Depression, and World War II. Ferguson's leadership transformed Newport News into America's premier naval shipyard. Under his direction, the yard built 7 of the 16 battleships in Theodore Roosevelt's Great White Fleet that circumnavigated the globe in 1907 to 1909. During World War I, Ferguson oversaw emergency shipbuilding programs that delivered 25 destroyers to the Navy. He also pioneered worker welfare programs. In 1918, concerned about housing for shipyard workers, Ferguson worked with the federal government to create Hilton Village, one of America's first planned communities. He formalized the Newport News Apprentice School in 1919, creating a training program that became a national model for technical education. The Apprentice School still operates today, training the next generation of shipbuilders. But Ferguson's most important contribution came in the late 1930s as war clouds gathered over Europe and
Asia. The Navy began planning a new
generation of aircraft carriers to replace the treaty-limited designs of the 1920s. The Essex class, as it would be called, would be the backbone of America's carrier fleet. Ferguson saw an opportunity to revolutionize warship design. He had a radical idea: use armor as structure. Traditional naval architecture treated armor as dead weight, protective plating added on top of the structural hull. Armor protected but contributed nothing to strength. Ferguson argued the opposite. If you used special treatment steel throughout the ship, you could create a vessel where every plate contributed to both strength and protection. Special treatment steel had been developed by Carnegie Steel around 1910. It was a nickel-chrome steel alloy with remarkable properties. It had the protective qualities of Class B armor plate, capable of resisting fragmentation and providing significant protection against shell splinters and bomb fragments. But unlike traditional armor plate, STS was ductile enough to be fabricated as structural steel. It could be bent, welded, and formed into complex shapes. It could carry loads like structural steel. Most importantly, it could be used throughout a ship wherever strength was needed. The problem was cost. STS was vastly more expensive than mild structural steel, perhaps 30% more expensive depending on thickness and specifications. Using STS throughout a carrier would drive the cost far above what the Navy wanted to pay. The Bureau of Ships initially rejected Ferguson's proposals as too expensive. Ferguson countered with detailed calculations. An Essex-class carrier using STS throughout would actually be lighter than a conventional design because the armor contributed to structural strength. That meant the ship could carry more aircraft, more fuel, more ammunition for the same displacement. More importantly, the structural redundancy created by using armor-grade steel everywhere meant that battle damage which would a conventional carrier might be survivable. You wouldn't save money on construction, Ferguson admitted, but you would save lives in combat and you might save the ship. Ferguson had powerful allies. Officers who had studied the early carrier losses of the war understood that survivability mattered more than any other factor. Lexington, lost at the Battle of the Coral Sea in May 1942, had been destroyed not by the initial Japanese torpedo hits, but by vapor explosions from damaged fuel systems hours later. Yorktown, damaged at Coral Sea, had been patched up in just 48 hours at Pearl Harbor and sent back to fight at Midway. She survived multiple bomb and torpedo hits at Midway, was nearly saved by her crew but succumbed to a submarine torpedo while under tow. Both carriers might have survived with better damage control systems and more robust structures. The Navy approved Ferguson's design with modifications. The hangar deck would be made of 2 5-in of special treatment steel instead of the originally proposed 1 5-in. The fourth deck forming the bottom of the hangar box would be 1 5-in of STS. The flight deck would sit on a framework of STS I-beams. The armor belt protecting the waterline would use 4-in Class B armor plate, backed by STS. Interior bulkheads throughout the ship would be STS where possible. The underwater protection system, the complex arrangement of compartments designed to absorb torpedo hits, would use thick STS bulkheads for the critical holding bulkhead that formed the final barrier against the sea. In total, each class carrier would use thousands of tons of special treatment steel. The exact figure varied by ship and is not clearly specified in unclassified documents, but engineering estimates suggested 3,000 to 4,000 tons per ship. The cost was enormous, but the result was a ship where every structural member contributed to survival. Ferguson pushed other innovations beyond just STS. The Essex class would have the most extensive compartmentalization of any carrier built to that time. Traditional carrier design used large open spaces for efficiency. Ferguson insisted on the opposite. Divide every space. Make every passageway a potential fire break. The Essex-class carriers were built with extensive compartmentalization throughout the ship, with hundreds of separate compartments that could each be isolated, flooded, or vented independently. The exact number of compartments is not specified in available sources, but the design philosophy was clear. You should be able to lose multiple adjacent compartments and still maintain buoyancy and stability. The firefighting system was revolutionary. Traditional carriers had a single fire main running the length of the ship. If the main was cut, entire sections lost firefighting capability. Ferguson designed a system of multiple independent fire mains, each fed by multiple pumps in different engine rooms, each capable of being cross-connected or isolated through a complex system of valves. The system used 9 separate fire pumps, each capable of delivering thousands of gallons per minute. If one section of the fire main was cut, flow could be rerouted through other sections. If pumps failed, other pumps could compensate. The hangar deck received an overhead sprinkler system that could deluge the entire space with seawater. Water curtains could be erected to create barriers against fire and smoke. The CO2 flooding system could pump carbon dioxide into fuel storage compartments to suppress fires. Emergency ventilation systems could pressurize spaces to keep smoke out or vent spaces to remove smoke. Every aspect of the damage control system was designed with redundancy with multiple backups with the assumption that damage would occur and systems would fail. But the ship had to survive anyway. The first Essex-class carrier USS Essex CV-9 was laid down on April 28, 1941, at Newport News Shipbuilding. Ferguson's Yard was the lead builder for the class. The ship was completed in just 20 months. Being commissioned on December 31, 1942, USS Yorktown CV-10, named to honor the carrier, lost at Midway, was laid down at Newport News on December 1, 1941. Her keel was laid just 6 days before Pearl Harbor. She was commissioned on April 15, 1943, with Captain Joseph J. Clark commanding. USS Franklin CV-13 was laid down at Newport News on December 7, 1942. Exactly 1 year after Pearl Harbor, she was launched on October 14, 1943. Sponsored by Lieutenant Commander Mildred H. McAfee, director of the Waves Women's Naval Reserve, Franklin was commissioned on January 31, 1944. None of Ferguson's innovations had been proven in combat when the first Essex-class carriers steamed into the Pacific in 1943. They were theories, calculations, design choices made in drawing offices and shipyards far from battle. The ships looked impressive, but would they survive when tested? The answer came in battle after battle throughout 1943, 1944, and 1945. They survived. When hit by kamikazes that would have sunk earlier carriers, they remained afloat. When fires raged through their hangars, the damage control systems worked. When bombs penetrated their decks, the compartmentalization contained the damage. The Essex class became the most successful aircraft carrier design in history, precisely because Homer Ferguson had insisted on building ships that could survive. Ferguson remained president of Newport News Shipbuilding until July 31, 1946. He retired at age 73, having seen his carrier survive every test combat could impose. After retirement, he remained active in the Newport News community. He was instrumental in founding the Mariners Museum in Newport. News, along with Anna Hyatt Huntington and her husband Archer, Monsieur Huntington. Ferguson served on the museum's board and helped build its collections documenting the history of shipbuilding and maritime commerce. He died on March 14, 1953, just a week after his 80th birthday. He received no Medal of Honor, no Navy Cross, no congressional recognition for his contributions to the war effort. His name appears on no warships. The general public never knew who he was. His contribution was too technical, too abstract, too far removed from the drama of battle to capture popular imagination. But the men who survived Franklin never forgot. In the decades after the war, Franklin's survivors organized reunions. The first reunion was held in 1947 in New York City. About 200 men attended. They shared stories, remembered the dead, and marveled at their own survival. The reunions continued annually for many years, then every few years as the survivors aged. The gatherings grew smaller as men died, but the bonds remained strong. In 1995, on the 50th anniversary of the attack, about 80 survivors gathered in Charleston, South Carolina. They visited the USS Yorktown Museum ship, an Essex-class carrier like Franklin, walking the decks of a sister ship, seeing the compartments, the fire mains, the structural details. They understood more deeply how they had survived. The engineering was visible in ways it had never been when they served aboard Franklin. The STS bulkheads, the multiple fire mains, the compartmentalization, all the design choices that had saved them became tangible. In 2005, 60 years after the attack, fewer than 30 survivors attended what would be the last official reunion. They met in Norfolk, Virginia, just a few miles from the Newport News shipyard where their ship had been built. The shipyard arranged a tour for them. These men, now in their 80s, walked through the yard where nuclear carriers were being built. They saw computer-aided design stations, robotic welding equipment, advanced materials, but the philosophy remained the same: build ships that survive. The young shipbuilders working on modern carriers were continuing the tradition Homer Ferguson had established. The survivors told the young workers a simple message: we're alive because men like you built our ship right. Build these ships right too. Someday men you'll never meet will owe you their lives. It was the fundamental truth of their experience. Engineering excellence translated directly into saved lives. Every man who walked off Franklin alive owed his survival to decisions made in drawing offices and fabrication shops years before the war. Shipyard arranged a tour for them. These men, now in their 80s, walked through the yard where nuclear carriers were being built. They saw computer-aided design stations, robotic welding equipment, advanced materials. But the philosophy remained the same: build ships that survive. The young shipbuilders working on modern carriers were continuing the tradition Homer Ferguson had established. The survivors told the young workers a simple message: we're alive because men like you built our ship right. Build these ships right too. Someday men you'll never meet will owe you their lives. It was the fundamental truth of their experience. Engineering excellence translated directly into saved lives. Every man who walked off Franklin alive owed his survival to decisions made in drawing offices and fabrication shops years before the war. Decisions about steel thickness, bulkhead placement, fire main routing, compartment design. The chaplain who fought fires, the engineer who kept the engines running, the navigator who organized damage control, all were enabled by the ship beneath their feet. Without Ferguson's innovations, their courage would have been futile. Franklin would have sunk and 800 men would have become 2,500 dead. The individual stories of Franklin's Medal of Honor recipients illustrate the human dimension of the ship's survival. Lieutenant Commander Joseph Timothy O'Callaghan received the Medal of Honor, the only chaplain in naval history to be so honored. His citation reads in part, "Lieutenant Commander O'Callaghan courageously led officers and men in fighting the fires and combating the damage. He braved dangerous and burning compartments, areas alive with exploding ammunition and threatened by flames to lead parties below and save lives. His stout heart, great courage, and cool leadership were the rallying point of the crew." After the war, O'Callaghan returned to teaching at Holy Cross College in Worcester, Massachusetts. He taught mathematics and physics, served as head of the physics department, and rarely spoke publicly about his Medal of Honor. He died in 1964 at age 62. His autobiography, I Was Chaplain on the Franklin, published in 1956, remains one of the finest accounts of the attack. Lieutenant Junior Grade Donald Arthur Gary received the Medal of Honor for his actions in the engineering spaces. His citation notes that he organized and led firefighting parties to the hangar deck and entered the No. 3 fire room to raise steam in one boiler. His prompt actions in risking his life to help save his ship were of great value in helping to prevent the loss of the vessel. The citation specifically identifies him as Lieutenant Junior Grade and notes his role in maintaining engineering power. After the war, Gary left the Navy and returned to civilian life in Ohio. He worked as an engineer for Ohio Edison, a power company, until his retirement in 1960. He received a letter from a young naval officer asking for advice about damage control procedures. Gary wrote back with detailed technical instructions and added, "Remember that systems don't fail. People fail. If you've designed your systems with enough redundancy, with enough backup, with enough alternative paths, then when people are at their limit, exhausted and terrified and ready to quit, the ship will carry them. Build that kind of ship." Gary died in 1977 at age 56. Commander Stephen Jerrica Jr., the navigator who organized flight deck damage control efforts, received the Navy Cross. After the war, he continued his naval career, eventually retiring as a captain. His experiences on Franklin informed his later work in damage control training. He died in 1993 at age 83. Captain Leslie E. Jarris remained a controversial figure. His strict discipline and autocratic command style had made him unpopular with many crew members before the attack. After the attack, he faced allegations that he had accused men who abandoned ship of desertion. Despite the fact that many had been ordered to abandon ship or had jumped overboard to escape certain death from fire, a Navy investigation found no wrongdoing, concluding that in the chaos of the disaster, communications had broken down and some men had genuinely believed abandoned ship had been ordered, while others had jumped to save themselves. Jarris was promoted to Rear Admiral after the war, but the controversy followed him. He retired in 1946 and died in 1975, largely forgotten by the public. But naval historians studying Franklin's survival noted that his decision to keep the ship moving, to refuse to give up, to drive his crew beyond normal limits was validated by Franklin's survival. Without both the engineering capability to survive and the command determination to save the ship, Franklin would have been lost. Franklin's post-war fate was inglorious compared to her wartime service. After arriving in Brooklyn in April 1945, she remained there for the duration of the war. Japan surrendered in August 1945 before repairs could begin. The Navy decided that with the war over and no immediate need for her, the massive repair costs couldn't be justified. Franklin was decommissioned on February 17, 1947, and placed in the reserve fleet at Bayonne, New Jersey. She remained in reserve for nearly 20 years, a ghost ship slowly deteriorating. The Navy Red designated her CVA-13 attack carrier in 1952, then CVS-13 anti-submarine carrier in 1959, and finally AVT-8 aircraft transport in 1961-1963. These were paper changes. Franklin never left the reserve fleet. She was too heavily damaged, and the cost of the extensive modernization necessary to make her useful for post-war operations was deemed unjustifiable when newer carriers were available. In 1964, Franklin was struck from the Naval Vessel Register. In May 1966, she was sold for scrapping to Peak Iron and Metal Company in Portsmouth, Virginia, for $228,000. However, the Navy repossessed her in June 1966 because of an urgent Bureau of Ships requirement for her 4 turbo generators, which were needed for other ships. Finally, on July 27, 1966, she was sold again to Portsmouth Salvage Company in Chesapeake, Virginia for scrap. On August 1, 1966, tugs began towing Franklin from her berth in the reserve fleet for the last time. As she moved down the channel, toward the scrapyard, a Coast Guard cutter passed by, rendering honors with 3 short blasts of its whistle, a naval tradition for showing respect. The cutter's captain, a World War II veteran, later explained his decision. That ship earned honors. I didn't care what orders said. She deserved respect. It was the last salute Franklin received. Franklin was cut up for scrap over the following months. Her steel, including the thousands of tons of special treatment steel that had saved her, was recycled into new construction. Some of that steel, according to Navy legend, though not officially confirmed, went into the construction of USS Enterprise, CVN-65, the first nuclear-powered aircraft carrier commissioned in 1961. The Enterprise served for 51 years, the longest service life of any aircraft carrier in history. When she was finally inactivated in 2012, naval historians noted that her survivability features, her extensive compartmentalization and redundant systems, trace their lineage directly back to the Essex-class design principles. The ship that refused to die had taught the Navy how to build ships that wouldn't need to prove their toughness the way Franklin had. Today, at the Naval History and Heritage Command in Washington, D.C. Trowse, researchers can examine War Damage Report number 56, the official analysis of Franklin's damage and survival. The document, over 300 pages of technical analysis, photographs, and diagrams, remains classified as restricted, not because it contains information about modern carriers, but because the damage control techniques it describes remain so effective that the Navy considers them operationally sensitive. Every damage control school in the Navy uses Franklin's survival as a case study. Every naval architect designing combat ships studies how her structure held together under impossible conditions. Every officer planning carrier operations understands that their confidence in taking risks and operating close to enemy shores, in pressing attacks home, rests on knowledge that their ship is designed to survive. The broader lesson of Franklin's story extends far beyond naval warfare. In any field where human lives depend on engineering, the same principles apply. Design for worst-case scenarios. Build in redundancy. Use the best materials available even when they cost more. Create systems that don't fail catastrophically, that degrade gracefully, that give people time to react and recover. Homer Ferguson applied these principles to aircraft carriers in 1940. They apply equally to airliners, to spacecraft, to buildings, in earthquake zones, to any human artifact where failure means death. The attack on Franklin killed 87 men in 30 minutes. The ship's survival saved approximately 1,700 more. That ratio, more than 2 lives saved for every life lost, represents the return on investment in superior engineering. The expensive steel, the extra compartments, the redundant systems all cost money and time and effort during construction, but they bought 1,700 lives in combat. No one can calculate what those men contributed to the world in the decades after the war. How many children they raised, how many businesses they built, how many students they taught, how many lives they touched. The ripples from their survival spread across generations, impossible to quantify but undeniably real. Franklin's story is ultimately about the invisible victory, the triumph that occurs before the battle in drawing offices and shipyards, where engineers and architects make decisions that determine whether men will live or die years in the future. These decisions lack the drama of combat. No one gets a medal for specifying thicker bulkheads. No one becomes a hero for insisting on redundant fire mains. But these decisions matter as much as courage under fire. Perhaps more, because they enable courage to succeed. Homer Ferguson never received a Medal of Honor for designing ships that saved thousands of lives. He never appeared in newsreels or history books as a hero. His contribution was too technical, too abstract, too far removed from the smoke and fire of battle. But the men of Franklin knew the 1,700 men who walked off that burning ship alive, who went home to families and futures, who lived long lives because their ship refused to die. They knew somewhere in the chain of decisions that led from conception to construction, someone had made the right choices. Someone had insisted on the extra steel, the additional compartments, the redundant systems. Someone had believed that men's lives were worth the extra expense. And on March 19, 1945, off the coast of Japan, those decisions proved more valuable than all the courage and sacrifice and heroism combined. Because courage without tools is martyrdom, sacrifice without capability is waste. Heroism without support is tragedy. But when brave men serve in ships built by capable engineers, when sacrifice is enabled by superior design, when heroism is supported by thoughtful planning, then victory becomes possible. Franklin proved this lesson at terrible cost, then brought 1,700 witnesses home to testify to its truth. The ship that shouldn't have survived became the ship that proved survival possible, and in doing so validated every decision that had gone into her construction, production,